really an honor to be here. A little terrifying to see quite a lot of people. This is more than I expected. But on the other hand, it's a strong showing of interest in the topic, and I think that's really remarkable. So it's very nice that there is a strong interest in the topic. If you attended the IQPC Towers conference in Bremen last March, and I can see some faces that were there, the first half of this talk today, I already delivered it there, so apologies in advance that you have seen a bit of it already, but I hope that you may find it interesting nonetheless. So I want to talk about two things. First of all, there was this 8 megawatt wind turbine tower benchmark, the so-called round robin exercise that we did 2 years ago. That I was very happy to see how much interest it generated and how, so first of all, how popular it was in terms of the number of submissions, and then how much interest it generated in the community, and then I will move on to some, not all, because there's too many to fit in 1 hour, some selected Eurocode shell-blocking developments, and this is specifically for Eurocode 3.6. I thought to begin just a little bit about the genesis of the round robin study. So I see my colleague Mark Seidel is in the audience. Mark Seidel co-organized the round robin with me, and so we've been working for many years together. Although today is only the second time we meet in person. Remarkably, that's the power of the internet for you, and the collaboration, the long-distance collaboration that it enables. And for a long time, so we sort of used to set one another little modeling challenges. So here is something I've been working on, you try and do it. And then we tried to do it, and often we got the same result, which was remarkable enough. So Mark, you used ANSYS, I used Abacus, but occasionally, we found that, this is a bit different. Your result is a little lower. Like, why is that? And then we dived into our models and our assumptions, and we tried to understand what the reason was for that. And so already in between two people working nominally on the same topic, we came up with quite a lot of variability. And I think then, at first, you invited, I think, 2 of your colleagues to also extend this kind of back and forth a little bit. So there was 4 of us working on the same topic, and that brought forth even more variability. Then came the pandemic, and so we focused on surviving for 2 years. And then in 2022, we thought, well, why don't we make this a much larger thing? Why don't we really extend this to as many people as we know, as many people as we can email? Mark, you gave the list of industry contacts, I gave the list of academic contacts, and we emailed about 50 people. Let's bring in, let's set a standardized problem for everybody. Let's create a template for them to put their results into it. This has been done in other fields. I don't recall we've ever done such a thing in shell-blocking, so perhaps it's time. A new Eurocode is on its way in. Let's see how well those let's see what is the health of the discipline. And so out of 50 people or so that we invited, we got quite a lot of replies, and of those who replied, I must say, mostly they made a submission. So we ended up with about 30 submissions, which is really remarkable. And that data is the basis of the first part of the talk. So excuse the long introduction. So this kind of a study where everybody is given a standardized topic and they're not meant to collaborate. We give some basic assumptions. There, deal with that. Do this problem the way that you think it should be done. This kind of a study is known as a round robin. And here is the benchmark, which would be familiar to many people in the audience I know. It is the upper part of an 8 megawatt wind turbine support tower. So we handed out nominal geometries. Everybody got given a diagram like this. It's a 36-meter high tower segment. It's quite a complicated shell. It's not a simple cylinder. There is a cylindrical. Oops, there is a cylindrical part, but then there is above it a kind of steeply tapering conical part, varying radii or varying diameters and varying wall thicknesses. So this is not a trivial shell. And the participants were invited to perform the whole gamut of computational analyses on these under two distinct load cases. You have the load cases illustrated here. So this refers to the flange at the top. So we had a vertical load, a transverse shear, a moment, and a torque. Now there were two load cases. One load case did not have the torque in it, and the other load cases had a torque in it. And so everybody was asked to do an LA, an LBA, an MNA, a GMNA, and a GMNIA. You don't know what these acronyms are. I will introduce each one in turn as we go ahead. Optionally, the participants were invited to do LBA-MNA assessments, or RRD. So RRD stands for Reference Resistance Design. These are two buckling design concepts that are Eurocode 316. I should say that we did not require participants to use Eurocode 316. This was if they knew it, if they were familiar with it, please apply it. But we, as you will see on the map of the world in a moment, just how wide the participation we had internationally. Many of our participants came from jurisdictions which do not use the Eurocode, so we did not expect them to be familiar with it, and we didn't want to reduce it, to restrict it to just Eurocode, because we wanted to see how does shell expertise the world over, how would it tackle this problem. Initiated, so the emails went out in April 2022. We got all submissions in by October. That's a lie. Lots of people asked for extensions, just like students do. So we got everything in by November, roughly. Then the next month, I spent processing, or we spent processing and writing it up. And so by January, we had submitted 2 papers for review, and by February they were accepted. So this was quite a fast turnaround. This was published as a 2-part pair of companion papers in engineering failure analysis, which I thought was the appropriate forum for a detailed case study. Part 1 was the round robin itself, that is the collection of all of the results with distributions. This paper has 29 co-authors, so being a co-author on the paper was a kind of an incentive to get people to contribute, and it clearly worked. So this is 29 co-authors, and part 2, this was just Mark and myself. This is a detailed work reference solution. It is what Mark and I could agree on is what we think is the right answer. And we make it quite clear that we don't think that this is the absolute undeniably right answer, but if you follow the assumptions we made, you should be able to reproduce this. And there's also quite a bit of Eurocode 316 commentary in there, as you'll see. I did this in Abacus, Mark in ANSYS, so everybody should be able to reproduce this using the software that they use. So that was part 2. And these are open access. You don't have to memorize the links. If you Google this, you will find it, and I invite you to read those papers. I was really so happy that we got such a truly international thing going here. So we got people from the US and Canada, here China, India, Oman, Turkey, Japan, Australia. Quite a lot of people from this place. I'm not sure if you've heard of it. We had a lot of submissions from Germany, some from Denmark, some from the Netherlands, and some from the UK. So it's a truly international exercise. there were quite a lot of participants from industry, which I consider particularly important since you guys are the main end users of the standard. More academics, though, to industry by a factor of roughly 2 to 1. I understand people are busy, but still I'm happy. So I will introduce the selection of the results, not all of them, and I hope you find them interesting. Oops. So the first set of interesting results that came out was just simply on good old-fashioned meshing. The assumptions that underpin the mesh that you use to create your model, since this will affect every single result that you generate. And looking at so we gave no guidance on how this should be meshed. Here is a normal geometry. Do what you think is right. And what was interesting about the meshing assumption was that there was an almost roughly even split between two distinct meshing strategies. The first is what I call the classical finite element approach of doing progressive refinement. That is, you begin with a coarse mesh, you get a result, some metric, then you refine that mesh, you look at the metric again, you see by how much it changes, and you keep refining until that metric does not change by very much anymore. So that introduces variability at the level of the metric, what you look at. So some people look at the displacement, some people consider the stress. Also, what you consider does not change enough. What is the tolerance that you take as good enough? So that varies as well. These are box and whisker plots. By the way, they show a distribution. Down here you have the 0th percentile, i.e. the minimum value. This is the 25th percentile. This red line is the 50th percentile, i.e. the median. This is the 75th percentile, so this is the blue box gives you an interquartile range, and up there is your 100th percentile, i.e. the maximum value. So everything, all of the results are from here to here. Most of them are there, and typically, sort of by convention, anything that is outside the interquartile range is considered an outlier. So that was one approach to meshing. The other approach to meshing is more of a shells approach to meshing, and that is, you do not do progressive refinement, but you go with a rule of thumb. And you ask yourself the question of what is the smallest feature that your mesh is trying to capture? And the smallest feature in a buckling analysis that your mesh is trying to capture is a local active compression buckling mode, which has a relatively well-defined wavelength, which you know in advance. So a wavelength is just a wave, and you can tell that, if you have a wave, how many elements do you need roughly to approximate a wave? And for linear elements, 10 per half wave is a good rule of thumb. And in many studies on shell buckling, that is the starting assumption for mesh design. 10 linear elements per bending half wavelength. And what is interesting is that the submissions that followed that relative to wavelength approach were, on average, led to finer meshes than those that follow the classical progressive refinement approach. I think the easiest thing to understand here is this figure. This is the spread of the degrees of freedom in the model, and this is the spread. So this is for progressive refinement, and this is the spread of degrees of freedom in the model for relative to the wavelength. The median is significantly higher. So this is, my view, a superior approach to modeling a shell. It is significantly less effort to design the mesh this way, because it's a pretty standardized meshing protocol that you assume, and it tends to lead to much finer meshes anyway. And I think these metrics, and many of these metrics were done on the basis of an LA, which is a linear elastic stress analysis, so not even a buckling analysis. It's not sensitive enough to the feature that matters. So that was the first interesting finding, is just some meshing assumptions. And since a mesh very much influences the results that you get, this is, if this is incorrect, then everything else will be incorrect. So that was the first set of interesting results. The next set of interesting results are the LAs. So LA stands for linear elastic analysis. This is not a buckling analysis. The aim of this is to obtain a reference elastic, linear elastic stress and displacement state of the structure. And the point of this, you must always do, I insist you must always do one of these, no matter what analysis you're doing, because this acts as a sanity check for your model. You have a tower, and you have a relatively simple point load at the top. This is a determinate cantilever. You should be able to tell the reactions from simple statics. If you get the reactions wrong at this stage, then there is no hope for any of your further results. Now, these are also box and whisker plots, and if you cannot see the interquartile range, that is a good thing. That means that most of the results were spot on, and the spread is very small. It's a very tiny bar. That means that most of the submissions got the reactions right. So this is the vertical reaction, this is the mass, vertical reaction, transverse shear force reaction, moment reaction, torque reaction. They were mostly gotten right, except for the submissions that you see here. Some are just completely wrong. We filtered those out from subsequent analysis because we wanted the variability in what comes to be explainable by differing modeling assumptions, but that were not attributable to mistakes. So we lost about 5 submissions this way. I don't name names, but yeah, there were about 5 submissions which we had to filter out. The black X that you see is the result given by the reference solution in every case. So the moral of this is always do an LA first. Use it to check your reactions and for a structure that is determinate, and you can compare them to statics. There really is no excuse for doing that. So that was that. LAs. Next were the LBAs. So these are linear bifurcation analyses. So there were 2 load cases, if you recall, LC1 and LC2. Load case 1 was one that had a bending moment at the top and a transverse shear force and an axial force. So this thing was predominantly under bending, and the bending moment increased with depth, and you would expect to have as a buckling mode, a localized buckling mode on the compressed side. And duly that is what the buckling mode was. Load case 2 has a torque on the top, and as far as the LBA is concerned, that dominates, and the critical mode there is a torque mode. So that's just to know what to expect. In terms of the spread of the results, most of the submissions, and by now these are the submissions these are the filtered submissions. So these would have been the submissions that passed the reactions check. They got this mostly right. So participants were also asked to submit a picture of the buckling mode, and everybody got this as the mode, so that was good. And there was a spread in results, and the spread of these results is really attributable to meshing. Because the coarser your mesh is, and some meshes were unfortunately quite coarse, and those you find okay. The coarser your mesh is, the stiffer your structure is. And the stiffer your structure is, that is, your shape is more constrained. You have to apply a higher load to achieve these same displacements. And unfortunately, this axial compression buckle is quite a small buckle, which means that you have to have quite a fine mesh locally where the buckle happens in order to capture it correctly. So if you have a coarse mesh, you will get a very coarse representation of this, and inevitably a much stiffer one. And there is a consequence to overestimating the LBA mode, and the LBA resistance as a consequence of a stiffer mesh. So far so good. Now, LC2, the torsional one, presented a few challenges because the torque dominates the system so much that if you were to reverse the torque, or rather reverse the loads, the torque acting the other way is as critical as the torque acting one way, because this kind of shear buckling can act in any axis, really. And that means that there is a critical eigenmode whose absolute value is similar to the critical one, but it has a negative sign. And many submissions reported this negative eigenvalue as the critical mode. This is not correct, because negative eigenvalue means that all of the loads are acting in the opposite direction. The torque, but then also the transverse shear and the moment and your vertical load now acts upwards. So it's an incorrect state to do. So anytime you get a negative eigenvalue in an LBA analysis, you must discard it. It is not a valid eigenvalue. So we had quite a bit of negative eigenvalues here. But for the submissions that restricted themselves to the positive eigenvalues, the predictions were good, and actually the variability was much less than with this mode, because the shear mode is a much longer wave mode, and you can get away with capturing it easily using a coarser mesh. So the same mesh as here it's much too stiff. For a long wave torsional mode, it is okay. So the moral of this is, if you get a coarse eigenmode, or rather, if your mesh is too coarse for the eigenmode, you will see that from the shape of the eigenmode that you get. It will be kind of jagged. And that is a signal to you as the modeler to go back and to refine your mesh and to do the analysis again. So these were LBAs, linear bifurcation analyses. Next came the MNAs. So MNAs are materially nonlinear analyses. They are the computational equivalent of a small displacement classical plastic collapse analysis. This is the computational way of doing that. I'm only going to show the results for LC1. The results for LC2 are a little different, but the conclusions are the same. Excuse me. So what I see here, in an MNA, you apply your load set. It's not an eigenvalue analysis. It is a nonlinear path tracing analysis. Because it's geometrically linear, there is no scope for buckling. You will not be buckling here. What you want to get is full plastic collapse. So it's the idealized reference full plastic collapse state. As you increase your load, so initially you will have a complete linear elastic response, but eventually somewhere begins to yield. And so your equilibrium path will begin to drop a gradient a bit. And as the yield spreads, the equilibrium path drops a gradient further, and eventually it should plateau. This is roughly the plastic collapse mechanism that you get. This point is the junction between a cylinder and a cone, and this is where you get the formation of a plastic hinge. That should be the idealized reference plastic collapse mechanism. So the black curve is the reference result, and the gray curves are a selection of the other results. And there is quite a lot going on here. Some of these they are simply incorrect. Some of them have very low plateaus. I'm not sure why that is. Some of them, there's quite a lot of them that sort of do follow the reference result, and they are more or less okay. And I think the variability around there is probably due to meshing. If you have a coarser mesh, you will once again get a slightly stiff response. But some of these results, they have just too high a gradient. And this is because the modelers here assume strain hardening as a model. And an MNA should never have strain hardening in it. It should be an ideal bilinear elastic plastic law, elastic rigid plastic root law, because that is what a small displacement plastic collapse analysis also assumes, and the two should match. So there should be no significant strain hardening in an MNA model. There is some allowance made for a very, very small amount, very tiny amount, just if your solver needs a little bit of numerical stability. I think it's E over 100,000 as the tangent modulus for strain hardening, but no more than that. So already that's a result. Now the question is, all right, given a curve like this, what do you take as your reference plastic collapse resistance, your RPL? And it should be the plateau value of the curve, the peak that you get. That's what it should be. And if you were to take that as the MNA result, then you would get a distribution like this. But that is not necessarily what many of the submissions reported as the RPL value. So the RPL that was reported, even for a more complete curve, is quite a bit lower. So there is one sin associated with overestimating your MNA because of strain hardening. There is another sin associated with underestimating it. And so I did follow this up. So quite a few submissions basically killed the analysis once they began to get a little bit of yielding. They said, okay, it's beginning to yield, stop. I'm stopping, that's my M&A result. So that's one sin. Another thing that was reported was, oh, I'm getting a lot of yielding. My software is reporting 10% yield. That's completely fine. It has to report that much. You have to develop a full plastic collapse mechanism. You will get such high strains. That's nothing to be afraid of. This is an idealized reference limit state. So that's okay. There's no need to terminate it early. So I will show in a moment why both overestimating and underestimating are bad, but for different reasons. So this variability here is attributable to differing material assumptions, but also to differing termination criteria. Now, why does this matter? So the second half of my talk will be on this thing, which is a capacity curve. If you are doing an LBA and an M&A, chances are it is because you're doing the LBA M&A buckling check, which is one of the 4 ways of doing a buckling verification in Europe 316. If you're doing that, then you will have to feed into your result into what is known as a capacity curve, or a buckling reduction curve, if you like, which is a relationship between the dimensionless resistance, which is the buckling resistance relative to the reference full plastic condition, or RMNA if you want, and the relative slenderness. So your MNA and your LBA results, they serve to establish a slenderness value, which localizes you on this relationship. Now, different things happen if either of these results are either too high or too low. So for example, if you overestimate your LBA result because your mesh is coarse, if your LBA is larger than it should be, then this is a larger number than it would otherwise have been. And because it's on the denominator, that means that this is larger, therefore this becomes smaller. So that means that your slenderness that you estimate will be higher than you should be, and in turn what you will get from that is a higher resistance from your buckling check. That's not a good thing. The other way, if you underestimate your MNA because you terminate it early, you will make the same result. This will be a lower number. You will get a lower slenderness, lower relative slenderness out of your analysis, and this will push you up the curve unconservatively. So that is one sin that can happen. The other one is well, if you overestimate your MNA because you have too much strain hardening, well then you will overestimate your lambda, and that in turn it can give you a result that is much too conservative. So neither is good. The moral of this really is that the LBA and the MNA matter if you're going to feed them into this design check, and they must be done right. Also, I mean, even if you don't do, even if what you end up doing is a GMNA assessment, I would never, I always, in my teaching, I say that you have to earn the right to do a GMNA. You have to build it up. You have to build up from an LA to check the reactions, build up from to an LBA, then an MNA, and then gradually build it up to a GMNA. Because every stage helps to build your understanding of what the system is doing, and at every stage you get to control for mistakes. Next set of results were the GMNAs. So these are geometrically and materially nonlinear analyses of the perfect structure. I should have mentioned so far all of the structures were perfect, nominally perfect, so the nominal geometries. GMNA, because you have geometric nonlinearity now, now this is an analysis that can give you a backlink limit state. It can predict that. So these are the results. The results. This is the load factor to the scaling factor on the complete load set against the transverse dip displacement for load case 1 without portion and load case 2 with portion. This one, the variability here was surprisingly small. These analyses, so yes, they will be affected by plasticity, but you will never get very far into the plastic range for any strain hardening that you may have assumed to matter all that much. So this will buckle, the buckling mode is relatively localized, and as soon as the buckling region begins to yield, it will just fail, it will just buckle. And so mostly these results are close both for both LC1 and LC2. I would point out, this is a personal comment of mine, that if you look at what happens in the post-buckling region, the answer is nothing happens in the post-buckling region as far as any of these submissions are concerned. No submission gave you a post-buckling path, not even the reference solution. Me working with Abacus, I was unable to make this go to give me anything like a significant post-buckling path. And I personally find it a problem that out of all of our otherwise quite powerful commercial solvers, Abacus and ANSYS, I mean, I had these problems 15 years ago when I was working on my PhD, and the solvers have clearly not changed in the intermittent time. I'm still fighting with Abacus to do the same thing that I was fighting with it to do 15 years ago. There is clearly no development being done on the solver side anymore. It's pretty much set in stone. And all of these ANSYS Abacus tools, they do change, but they just look fancier. But the underlying solver hasn't changed in 2 decades, at least for buckling. This should give you a post-buckling path that sort of drops down and then begins to do this. But in all of the analysis, in all of the submissions, nobody gave a correct post-buckling path, not even me. And now we come to, I suppose, the most interesting one out of this set of results, which are the GMNIA. So the geometrically materially nonlinear analysis with imperfections. Once you have the I in here, this opens up a whole new world to you. We gave no guidance as to what the imperfections should be. We only said that this structure will be built to an excellent quality class. It will be built very well. So that for the people who know the Eurocode, this was a hint that go for fabrication quality column as class A. For those that don't, I don't know how they understood that. So already we asked for a picture of what you think the failure mode is. This is a selection of what was submitted as failure modes for LC1 and for LC2. And it is very, very, very different. Also, what is understood by what is an illustration of the failure mode was different. Is it a stress state? Is it a buckled state? Is it an incremental buckling mode? There was a lot of variability there. But this is a cumulative distribution of all of the GMNIAs that we had. The black line is for load case 1 without portion. The hollow line is for load case 2 with portion. I mean, the community could not decide whether this tower is safe or not, clearly. Any GMNIA less than 1, that means that you cannot achieve your full set of design modes that you're applying. Anything greater than 1, it means you can with some reserve. I mean, okay, so the variability comes from different imperfections that people assume, but also from different ways of applying an amplitude. What does an amplitude mean for that imperfection? What number to take? Which version of the Eurocode did you look at? Because there was the 2007, the 2017, and now the 2024 version. All of them give a slightly different outcome. It was also what do you take as the termination point. Is it which point on your equilibrium curve is that? All of these things combined to give you this variability. Not everybody used the Eurocode. So that's another source. But this is a really remarkable spread. It's a little alarming, though, how widely spread this is for something that should be a relatively well-defined thing. So I have here a comparison of these box and whisker distributions now for both load cases, the LBA, MNA, GMNA, and GMNA. And the largest variabilities come in the for both load cases come in the MNAs and in the GMNAs. I have down here what I call the dispersion coefficient, and this is a kind of a non-parametric version of a coefficient of variation. This is the interquartile range normalized by the median. It is largest for the MNAs and the GMNAs. The MNAs because of the different material assumptions and the different termination criteria, and the GMNAs are for that, and also for all the different assumptions relative to imperfections that you can make. I thought to comment that I think in the whole Eurocode reliability framework, there's partial factors on everything. There's a factor for uncertainty in the geometry, uncertainty in your model, uncertainty in your material, but there seems to be another source of uncertainty here, which is uncertainty in interpretation of a rule, which I think contributes to quite a bit of what is seen here. And I think this is quite remarkable and actually a little alarming to me. I want one day to repeat this exercise for a much more targeted, so not yet, but in a couple of years, once the new FPREN 2024 has become adopted, and just to repeat it solely for users of the Eurocode, following the Eurocode rules, quite carefully, and the same document. Here is your thing, follow the same document, tell me what you get. I will be very interested in doing that after doing this. One thing that transpired from all of the GMNAs is the matter of interpreting an imperfection amplitude. It's the question of what do you understand by an imperfection amplitude versus what the standard understands by an imperfection amplitude, and I suspect that the two might not necessarily be the same thing. And there's an important reason for that. So one must make a critical conceptual distinction between something that I call the mathematical amplitude. Unless you have scanned the structure and are using the real perfect geometry, chances are you're idealizing your imperfection in some way. You're taking some model of an imperfection and you're putting it into your software. And the amplitude of that imperfection model is what I call the mathematical amplitude. In your model, you know what a reference axis is. Typically, it's whatever the perfect structure was. And the mathematical amplitude defines the amplitude of your imperfection relative to that perfect state. That is not what the Eurocode means when it talks about an amplitude, and the amplitudes that it prescribes for use in GMNA are not the same as that. What the Eurocode talks about are tolerance amplitudes, because this relates to the amplitude that you get when you measure the shape of a real structure in the field. And that is a different thing. And the two, this is what is controlled. This is what Eurocode 316 gives you numbers for. This is what you must match. But what you directly control is the mathematical amplitude. And you have to be able to relate the two. So given a given delta m, what is the delta naught that you get? I will illustrate. And it does this because if you do not match the two in this way, then you have no link between the imperfection that you assume in your model and something that you can actually measure on the finished structure. Because remember, on the finished structure, you don't know what the original perfect structure was. You have no reference axis. So you have to create a reference axis by placing a gauge on the structure. And so there are different tolerances that you have to check. Let's say we're talking about the dimple tolerance, which is you look for bumps on the completed structure and you place a gauge gauges of set lengths. The lengths are related to buckling cap wavelengths for a shell of that radius and that thickness. And once you place a gauge against the wall, you have created a reference axis. And if you drop a perpendicular from that to wherever it hits the wall, that will give you a tolerance amplitude. And that is what the standard controls. This is a little cloud. This is an imperfect. It's from a laser scan of a shell. Actually, a spiral welded tube in Karlsruhe, and there was a big bump on it. So it's a nice thing to illustrate this on. So how does this relate to now imperfections assumed in GMNIA? Well, let's go with the most popular imperfection model of them all, which is the LBI Eigenmode. This is a close-up of the Eigenmode that you got for load case 1. You have these little ripple deformations here associated with local buckling on the compressed side from bending. The dashed line is where the perfect structure was, so that acts as the reference axis. If you try to sort of relate those LBA deformation to that, then delta M will be the distance of the max radial deviation relative to where the perfect structure was. That's the mathematical amplitude. But the tolerance amplitude is, well, you have to find, if I were to place a gauge on here, and the worst place to place a gauge is here, in between the two outer bits, and the perpendicular to that gives you your delta naught. This is what the standard says you have to meet. This is what you actually control. It's actually worse than that, because, at least in Abacus, you don't even control this amplitude. What you control is a scaling factor on the Eigenmode shape. So first of all, you have to know, for a given scaling factor, what is the delta M that I achieve? And for that delta M, what is the delta naught that I achieve? And there are calibrations that you can do that relate one to the other. And once you have those, then you can design your scaling factor so that it achieves the target tolerance amplitude, which is what has to be European compliant. Part 2 of the round-robin study is pretty much 60% on exactly this, an illustration of this calibration, just because it's an unfamiliar procedure. This is for an LBA eigenmode. I make no judgment about LBA eigenmodes as models of imperfections generally, other than that they're awful. More awful is a torsional eigenmode. I know some people are forced to apply this as an imperfection. It's by no means a model of any imperfection ever, but there you go. This can be calibrated in a similar way. So you have here the deformations. They follow the circumference, and you have here what was the original cylinder. So delta M is relative to the position of the original cylinder. As a modeler, you know where that was. Delta naught is what is the tolerance amplitude if you were to place a gauge. And for deformations like this, the gauge is curved. It has the same radius as the cylinder at the point, and you can once again relate the two to one another, and also to the scaling factor. And the correct Eurocode compliant calibration does this. So if this is unclear, I invite you to look at part 2 of the round robin. We give algebraic expressions to aid in this, and generally in recognition that you know more and more modeling of this nature is done in some way automatically. I would expect that people write some sort of an automation macro to do this. Just the final point on LB Eigenmode imperfections. This is a spread of the first 100 eigenmodes for load case 1. The colors identify roughly where in the tower most of the deformations associated with an eigenmode are. The white ones are down here, red ones are a bit lower, blue ones are a little higher, and then there's the green ones up here. And the point of this is simply to show that the very first eigenmode that you get will not necessarily give you a critical imperfection as far as GMNA is concerned. If you take this eigenmode and if you scale it appropriately, you will get this as the GMNA load factor, with the I being this imperfection. But if you kind of look a bit higher up to the higher order modes, and the standard does encourage you to do this for exactly this reason, then mode number 13, which corresponds to the first time that buckling deformations appear up here, actually gives you a bit of a lower GMNA. And unfortunately, there's no shortcut to knowing which one does this. It needs to be an exhaustive search. So that is the first part of my talk. How am I for time?
We have 20 minutes.
20 minutes, that's perfect.
Or 15 if there was many questions.
There's no question. I'll talk 20 minutes so that nobody can just have a little pause and have some water. So I wanted to pivot now away from the round robin to talk about something new. So this is the capacity curve framework. I mentioned it briefly, but I want to talk about it a little bit more. This framework underpins every buckling resistance function in Europe 316. I would think of it as a kind of a skeleton for the physics, an assumption that, it's an assumption that for different slendernesses, buckling looks like this. So it is a relationship between a dimensionless resistance, which is expressed here as a knockdown relative to the full reference full plastic condition, loosely speaking the M&A result. It's a relationship between that and the dimensionless slenderness, which is defined much as it is in numerical 3.1 as the square root of the full plastic resistance relative to the elastic critical buckling resistance. And it identifies three regions. You can be in the high slenderness region where buckling is expected to be entirely elastic. You can be in an intermediate slenderness region where buckling is elastic plastic, and then you can be in the low slenderness or the squat, stocky region where it isn't really buckling anymore, it's plastic collapse. This here is an alternative view of the same thing, but just with the horizontal axis expressed as the ratio of the resistance, the characteristic resistance, to the elastic critical buckling resistance. The slenderness here is then kind of an implicit variable. It is advantageous to look at this relationship in this form, particularly when you're considering elastic buckling, because what you're essentially showing is this ratio. It becomes that, and it often becomes a vertical line, and it makes this point very easy to identify, as we will see. So, as mentioned, all of the resistance functions for buckling are expressed within this framework. And what this framework assumes is that in the elastic region, there is something responsible for buckling there, and that is captured by two so-called capacity parameters which are relevant for the physics there. So elastic buckling is affected by a geometric nonlinearity, and there's a parameter that accounts for that, which is alpha g. And it's also affected by imperfection sensitivity, which is accounted for by alpha I. So alpha I and alpha g govern the elastic buckling behavior. They are the two capacity parameters that act here. Kind of going up the curve this way, here is where you have elastic plastic buckling, and there are different aspects of the physics there, and they're captured in this using different parameters. So you have a beta parameter that identifies where plasticity first begins to influence the relationship, and then the shape of the relationship itself, the severity of the elastic-plastic interaction is captured with the eta parameter. And then going here, the point where this hits, the curve hits the full reference to plastic condition is captured by another parameter called lambda naught, this quotient with relative slenderness, and we even have a provision to give it some, for the buckling resistance down here to benefit from some hardening effects, either geometric or material, and there's a parameter phi h there. So there is an algebraic form that models this entire relationship. And it is a three-part form. You have one equation when you are in the fully plastic region, another equation with different parameters when you're in the elastic plastic region, and then another equation with different parameters if you are fully elastic. So the capacity parameters are highlighted in red, and they are established that each system that is characterized within this framework in the annexes, Annex D and E, has its own set of these capacity parameters. So a cylinder under uniform axial compression will have its own set of capacity parameters, a cylinder under bending, its own, cylinders under torsion, under uniform external pressure, and also spherical shells under uniform external pressure. All of them have their capacity parameters that represent that system and that give you this full relationship. And now, when you want to use it, what you need to do is to identify where you are on the relationship. And these are where the two reference resistances come in that you must compute for your system. That is your reference plastic collapse resistance and your reference elastic critical vacuum resistance. Once you have that, you have a slenderness. You find where you are, and then you use that equation, and that gives you your chi, which is your knockdown on the full plastic resistance, to give you your characteristic resistance. And then you combine it with a partial factor to give you a design resistance. So as of 2024, for carbon steel shells, this is the most complete framework. And research, and a lot of what I do is establishing these capacity parameters for different systems. And it's quite complicated to do. I wanted to show you, so this is a plot of the capacity relationships for uniform radial compression, so a cylinder under uniform radial compression over the years. And the old timers among you will recognize these relationships. So this is the dimensionless resistance on the full plastic condition here, and on the horizontal axis is the slenderness. This is the version this is what it looks like in the 2007 version. So let me just say how to interpret this. The blue kind of cloud is the full extent of where you can be. And you can either be class A, this is fabrication tolerance quality class A, which gives you one set of imperfection assumptions, or you can be class B, or you can be class C. So your resistance, qualified resistance will never be outside of these bounds. It's either A, B, or C. Also shown for flavor is the old DIN rule, which is shown in red. It wasn't quite expressed in the capacity curve framework, but it was the precursor to it. The blue, the 2007 rule, you can see down here, or I'm drawing your attention to down here. It was quite a conservative rule, particularly for the elastic region. So we had quite low predictions for the elastic buckling. In 2017, we changed that a bit. We brought that up so that it isn't so unnecessarily conservative in the elastic region. Fortunately, there was a mistake in the standard in 2017. This bit of the curve is represented by the eta naught parameter. It was a little higher than it should have been, which is why this descent of the full plastic condition is a little liberal. That was, unfortunately, a mistake in the standard, but we have since fixed that. So now the 2024 rule, this is what it looks like. This part of it is corrected, but the elastic part is the same as in the 2017 rule. So this is how the original compression curve has changed over the years. And this is a very important curve because this is used a lot in designs, and so many systems can be related to it. Next one along is, or if you like, the next most related one is the curve for the cylinder under uniform bending. This only began in 2017. The previous standard, the 2007 version, did not have a separate curve for this. And this also underwent a bit of a change in 2024. And it was also made to be a little bit, this was felt to be a little too unconservative, and we brought it down a bit, and we also made it more complete as a formulation. And I thought, you may be asking, what is meant by a resistance here as the input in the capacity curve? And if I take us back to here again, it's an interesting question because many things can be understood by a resistance and still be an input into this curve. And that is because this curve, the formulation is completely dimensionless. So the resistances only occur as a ratio. So they can have different dimensions, and indeed in the different buckling design checks that you have in Euro 316, they assume that the resistance means different things. But because this formulation is dimensionless, they can still remain inputs into the framework. So to do a buckling check in Euro 316, there's 4 methods, of which one is designed by GMNIA, which bypasses this. But one of the checks that you can do is a stress design check. So you're doing a check at a point. You're obtaining usually the membrane stress state at a point. And this, then the input into the capacity curve is a stress with dimensions force per area. And your R critical is the classical elastic critical buckling stress. And your RPL is your yield stress. And the RK, the characteristic stress that you get out, the characteristic resistance is then a characteristic stress. And you do a check at a point that this does not, that your memory stress does not exceed the design stress. If you're doing a design by reference resistances here, the check is not done at the level of the stress anymore, but at the level of the net load that you apply on the shell. And if it's a cylinder under axial compression, then you are applying a net resultant force on the shell. And that is your input into the framework. So then the resistance is a force with dimensions of force. Or if you're applying a moment, the input into the framework is a moment. And that's okay, because they only appear as a ratio. And most abstractly, in my view, is the LBA-MNA method, where you can be applying potentially a very complicated load case onto your shell, and your resistance is then a proportionality factor on that complete load set to give you a particular limit state. And then the input resistance are those proportionality factors, and that's okay because it's dimensionless. And then the output that you get is a proportionality factor at which you get a nonlinear buckling limit state. And because the LBA-MNA method is the most abstract method, then the question is, well, if I have a potentially very complicated load case, and I want to feed this into the framework, what capacity curve do I choose? Because almost certainly you will not find a curve that corresponds exactly to the system that you have. It is our intention to complete the coverage in annexes D and D, but it takes a long time to develop good rules. So which curve do you take? Like even for the towers that you had, we had axial load, we had transverse shear, we had moment, we had torque. We don't have a capacity curve that takes all of those as an input. And so in recognition of this, LBA-MNA tells you that it gives you a default value. It tells you a default capacity curve to take. And if you look in the 2007 version of the standard, this is clause 862, paragraph 11, which says, and I quote, "If you do not know any better, take the values for an axially compressed and stiffened cylinder." Because on the grounds that this is one of the most conservative capacity curves that you have, so if you do not have grounds to take something different, take the most conservative thing. And what this says visually is well, okay, you've done your LBA, we assume correctly, you've done your MNA, this has given you a dimensionless slenderness, this has placed you somewhere, take the curve for axial compression, and that will give you your resistance. That will give you your characteristic resistance. So that was the rule in 2007. And in 2024, we changed it a bit. And this is now clause 972.4, paragraph 10, and it says, If you do not know any better, and you are in the elastic slenderness range, continue to take the capacity curve for axial compression. But if you are in the elastic plastic range, take the curve for bending. And when this was going through the whole Eurocode commentary, this drew quite a few comments as to why did we change this? And I thought to just explain in the last 10 minutes that I have why we do this, why we introduce this rule. Are you ready? All right. So first is to show by direct comparison on the same plane, and you can do that because it's a dimensionless formulation. The marginal compression capacity curves are correct, and the blue ones are the ones for bending. And in the elastic plastic regions, you can see that indeed the curve for bending can be more conservative than the curve for axial compression. Although here it is still very much still the curve for axial compression that is more conservative. So this is a real effect. So I wanted to first just tell you how these capacity curves are established. And the capacity curves are established computationally using GMNIA, very, very carefully done GMNIA calculations. The capacity curves are generated at a constant dimensionless length value given by dimensionless length parameter omega, L over R squared root 2 over R. If you keep this constant, then you keep non-wave effects constant in the cylindrical shell. Going from here, so these are the thickest ones, excuse me. The thinnest ones here, you reduce R over T, and that brings you back up the curve up to here where you are in the stocky region. And all of the curves are done at a constant imperfection amplitude. Omega, the dimensionless length is kept constant, imperfection amplitude kept constant, radius to thickness ratio is the thing that is varied to generate a curve. And depending on which parameter you're trying to extract, the traditional view of chi versus lambda might be more advantageous, or the chi, this is nk over rectoplastic position versus nk over empirical, the modified view might be more interesting. So how do we establish lambda naught? Well, wherever your data points cross the full plastic condition, that identifies lambda naught for you. If you do a little projection to the vertical axis, conservatively that will then give you chi h. Interestingly, we actually do two capacity curves for each set of condition. One is a GMNIA curve, and the other is a GNIA curve. Because in the elastic region, they must be identical. If it's purely elastic vacuum, then even if you specify material nonlinearity in the model, it shouldn't have an effect. So those two curves must give you the identical relationship. But as you get stuck here, at one point they should begin diverging. And this is a very, very accurate way of identifying this beta value, which is the resistance at which plasticity first begins influencing your curve. Because it is where your GMNIA and your GMNA curves first begin diverging in the onset tolerance. Once you've established that, at the same point, if you're looking in this plane, you can identify what your alpha G, alpha I value is. And from that, you get the derived value lambda P, which is the slenderness at which all this happens. And then is the question, well, how do you characterize the elastic plastic region? You could do just the least squares fit, but we don't really do that. We want to be a little more conservative, and we take values of eta naught and eta p, which give you a kind of a cushion, a lower bound under the curve. So, main takeaways from this is the beta value and the alpha value. Am I?
Well, getting close to the end.
Getting close. I am actually almost finished. So these are capacity curves for the perfect shell, perfect cylinder of a non-ovalizing length. So none of the nonlinearity that you see here is due to ovalization. The red curve is axial compression, and the blue curve is bending. So the question now: at what point does does a cylinder under axial compression get affected by yielding, can be answered by considering it just as a beam. Because the point of first yield is the point of full yield, because the stress state is uniform. Therefore, the first point where you are affected by yielding is already the full plastic condition. And that translates into a 1 minus beta value of 1, which you're right up there. But for bending, it's different, because the first point where yielding affects bending is quite a bit sooner than the condition for full plasticity. And this value here, which you can check from beam theory, is about pi/4, which is about 0.79. So you must get, in a like-for-like comparison of curves, you must get yielding begin much sooner from the bending curve than you must from the axial compression curve. And that means if you're looking for a default curve that is conservative, you have to go for the bending curve as the conservative one, because its 1 minus beta value is necessarily significantly lower than the 1 minus beta value for axial compression. Do I have time for another interesting point?
Yes.
Everyone will, the thing will be that we have 5 minutes fewer for
that's okay.
coffee, and I think everyone.
That's part of my plan, not to have. I just thought, since I have you, and I'll never have your attention again, isn't it interesting that the curve drops so steeply? Because it doesn't have to. Yield has just happened, and all of a sudden the curve has dropped really quite strongly. That means that there is a very strong immediate interaction between yielding and buckling. Isn't that interesting? And the reason for that is because, well, you have a little bit of the circumference initially that is yielded. It's just a little bit. But remember, this is a thin shell, and you're going thinner to thicker, and this is still buckling under bending, so locally you have conditions that are similar to uniform axial compression, which means that you get a buckle that is an axial compression buckle, which is very small. So even though not much of the circumference is yielded, the buckle isn't very small either, and that little bit of the circumference actually happens to cover most of the buckle. And then as you go thicker from right to left, the yielding portion grows, but the buckled portion grows with it, and it is also almost completely covered by the yielded region. So you have buckling essentially contained within the yielded region for a long time, until you increase. As a matter of time, these are the complete capacity curves for varying imperfection amplitudes, and you can see that this premature yielding effect persists for deeper imperfections as well, and for that reason 1 minus beta is lower for bending uniformly, regardless of delta T. But if you look at the vertical axes, which represent elastic imperfection sensitivity, this vertical line, it is still lower for axial compression than it is for bending. And I have here plotted alpha I. Alpha I is lower for bending, for uniform compression than it is for bending. 1 minus beta is lower for bending than it is for uniform compression. There's some funny things happening here because you have extremely imperfect shells there. There's another effect there which I won't go into. But this is the justification for that rule, which I think is a nice piece of mechanics to end on. I can't promise that every rule in the standard has such an interesting story behind it, but that one certainly did. Thank you for your attention.
Thank you very much for your very dense, very impressive presentation. I think at this early stage of the morning, everyone now is into the topic, coming back to that very, very comfortable.
Either fully awake or fully asleep.
Yeah, so we're a little bit late, but maybe 2 or 3 questions, of course, we should have them. Professor Schaumann, please.
I have 2 short questions. First,
you get a microphone.
Concerning the round-robin test, did you specify the stress-strain relationships? For all applicants? Or
Did we specify? We said, we just gave a yield stress value.
and the
Okay,
yield
let's look at
model?
that. We didn't say that it shouldn't have strain hardening or that it should.
Okay,
But
okay.
we just gave an E modulus and a stress value, a yield stress value.
And second question, what you call the water form.
Yes.
Is that introduced in the new version of the Eurocode?
The rotor form has been in there since the ENV 1997. It's just a mathematical rearrangement of this. Oops. It's just a mathematical rearrangement of this. It doesn't introduce anything new. It's just a different view.
Mm-hmm.
The designer doesn't actually use it. It's more a research tool to extract these parameters more conveniently, but the designer and the curve is given in terms of lambda, in terms of the slenderness. Thank you.
I love you all more than ever. I have a question regarding to your slide number 25. It's on the beta, which
Yes.
indicates first yield or limit between elastic region and partial plastic.
It indicates the point of this curve where plasticity has a noticeable effect.
Yeah.
So I'm sure a little earlier there might be some localized surface yielding somewhere, but if it doesn't have a significant effect, this won't affect the resistance much.
Okay. My question is, we have three classes, we have three tolerance classes,
Yes?
and we have only one beta. I think this doesn't fit.
You don't. Beta, so it depends on which system you look at. They have more or less complete coverage, which turns into more or less complete dependencies. All of these things are functions of the imperfection amplitude, which make them into functions of the tolerance class.
Thank you.
But you're right. They shouldn't not be dependent on the tolerance class. I think
There was one more question.
Yeah, a very short one. Yeah, good morning. Michael Rode from BAM. Thank you very much for this interesting presentation, because I'm not really involved in this topic yet, because I look more from the materials processing side in terms of welding. Some years ago we had a project with I-girders or I-beams, I don't know how you call it correctly, where we looked for the effect of residual stresses to increase the load capacity by, let's say, assessing the factors that you have to use from the construction side of view. Is this involved in such kind of modeling as well?
We don't look at residual stresses pretty much anywhere. It's quite a difficult thing to incorporate into a model like this.
I see.
There was one.
Perhaps I have to add, my motivation is because we always look for application cases
Yes.
to increase the capacity by high strength steels like that. And at that time, at least for I-girders, it was possible to increase the load capacity by increasing the factors you have to use for safety regulations, what you have to consider if you weld them. And just for perhaps is this in the focus somewhere, just to. Because I don't know if it is like that. That's my question. If this will play, if this already played some role, this is what I.
It doesn't play a role currently, not in the formulation of the rules. It's whether high-strength steels will play a role in the future in Colloquium 6. I suspect not in the immediate future.
I see.
Mark, you might have a different view. No.
So that looks like a perfect communication topic for the next coffee break.
Definitely.
So therefore, thank you again, Adam, for the great presentation. Thank you very much.